let's try another example. This one again involving friction and changes in velocity, and looking how we can apply our work theorem to this. So in this case, this is number 62, again from chapter 7. And in this case, I have a ramp, looks like this. And the ramp drops 4 meters. And the package folks are using this ramp to deliver packages to a truck. So I have a package right here, and it falls down this slope from point A, slides down the slope from point A to this point B, and then it slides, continues to slide to point C where it comes to rest. And when we, let's say the package has a mass of 200 grams, okay, we notice when it reaches this point after falling down this hill, it has a velocity of 8 meters per second, and then it slides to a stop here with a velocity of 0 meters per second. And then the question is, what's the work done by friction? And the second thing is, what is the coefficient of friction between B and C? Now, you could see this as an engineering problem, because if you've got a package up here and if there's too much energy lost by friction, you're going to wind up heating the box or something like that. Maybe that's not desirable. And here, maybe you want the box to slide to a stop right at that point. You'll want to design this with a surface that has the appropriate coefficient of friction. So those might be two parameters that you're trying to work out. So our strategy here is, again, we're going to be using work and energy, and in particular we're going to be looking at how work is converted into kinetic energy, and then we're going to use that to figure out the coefficient of static friction. Okay. So the first thing you'll notice when you look at this is that we need to break this problem into two parts. We need to break it into the part where the box is falling down this ramp, and then we need to break it into this part right here. So I'm going to just focus on this part, and I'm going to notice that we have a certain amount of starting energy, and that's going to result in a final kinetic energy and some energy lost to friction. Okay, so let's go ahead and let's first work out how much work occurs between A and B. And if I think about that, I can say, well, we're starting at a 0 velocity up here, and we're winding up with a final velocity here. And the amount of energy we have available to us is going to be the mg times the distance the object moves in this direction. So that's going to be the work by gravity. So we start by saying, well, the work by gravity is just the force, mg, times the distance. We'll call that h, which is 4 meters. So that's the work that's done as it falls from here to here. But there's still some kinetic energy left over when it does that, and so the difference between this and the kinetic energy here is going to tell us how much energy is lost. So I know the kinetic energy at point B is equal to 1/2 mv squared, and I know m and I know velocity. So that means that the work, there's one component of work that we haven't talked about, and that's the work done by friction. So that's going to be the difference between these two, and that means that the work done by friction is going to be equal to mgh minus 1/2 mv squared. Okay, so I can go ahead and compute that just to get an idea of what that is, and that's going to give me, let's see, we've got 200 grams, so I'm going to get 0.2 kilograms. And that's going to be, I'm just going to use 10 meters per second squared just to keep the numbers round. Then we'll put a 4 in here, like that. And then I get minus 1/2 0.2 kilograms times 8 meters per second, and that whole thing is squared. And so if I do that, let's just bring out the 0.2 so I don't need to worry about that. And I get 40 from that term. And I get 64 divided by 2 is 32. So that gives me 0.2 times 8, which is the same as 2/8 over 10. And that's 16/10, which is 1.6, and our units are joules. So not a whole lot of energy is lost, so we don't need to worry about that so much. So we can think about that in our significance. And if you calculate, what you can imagine doing is saying, well, what would the velocity be if there was no friction? We would just set these two things equal to each other, and we'd find that this is a relatively small amount here. So you could do that as part of your significance. The second part of this question is computing the coefficient of static friction of the bottom part of the ramp. So this is going from B to C. Make the illustrator B to C. Okay, and we start with a velocity of 8 meters per second, and we go to a velocity of 0. Okay, so we have, again, a frictional force acting over a distance. That's our distance d, and we know that distance. It's given in our problem. That distance is 10 meters, according to the figure. Okay, so I'm going to write down the work done by friction in this case is going to be equal to the force times distance. Our force is mu times n times our distance there. And we know that n in this case is just mg because that's balancing our gravity here. Okay, so this is equal to mg mu d. That's the work done by the friction. The total amount of energy we have available is our kinetic energy at B, which is 1/2 mv squared, because we don't have any leftover kinetic energy here, so I can go ahead and set those equal to each other. I get 1/2 mv squared is equal to mu mg d. Our masses cancel, so we don't have to worry about those, and I wind up with mu being equal to v squared over 2 g d, like that. And so that's just I get 1/2 of 64 divided by 10 for g, keep the math simple, 10 for d, so that's going to be 32 divided by 100, which is equal to 0.32. And for our significance, you'll remember from some of our other discussions that this is a reasonable friction coefficient.